Hi, good afternoon. My name is Melissa. Welcome to my stream. I am an ecologist in the UK, and you're probably asking, why are you doing this? Because this is my first stream. A little bit nervous. I can't hide that all that much. Um, the reason I'm doing this is there's been an increase in science denialism. Um, and for those who don't know, that's essentially where people go and look at the current scientific theories and bear in mind that theory means something completely different in science than it does colloquially. And we'll get to that because that's kind of what this is all about. But the it's the denial of evolution, the denial of vaccines, um, a lot of other medical procedures. Being a trans person, I am well aware of this. Um, But yeah, hopefully this is going out to my YouTube audience as well. This is also my first video on there. Oh joy. Yeah, let's get into this because a lot of AI videos are popping up, and it's oh yeah, this thing happened in this time, and it's like the animal didn't even live in that period. I think I saw one that said Megalodon ate T-Rex, which you know separated by massive extinction to begin with, not to mention 30 million years of time, roughly. So, yeah, hey, rather than be around the bush, let's just crack in, I guess. Um, and a lot of you are probably looking at this and saying, well, this title looks very conspiratorial, and is kind of, I guess it's clickbait. But what this is essentially a take on the birds aren't real conspiracy that came out in 2018, which posited that birds were drones and yeah, they're using power lines to recharge, and that the government was using birds and floating quote marks to watch people. Um, Interestingly enough, this is a satire of a conspiracy. The person who brought it out um, was essentially using it to show how conspiracy is ridiculous, and yet people will pick up on it because it plays to that sort of I don't know what's going on, so therefore this thing sounds right, or it sounds interesting, or it sounds better than the alternative. So we'll go for that. And I'm pretty sure there are actually people who believe birds are drones. But that's kind of what this is riffing on. This is Fish Aren't Real by Maid Melissa, yours truly. And yeah, let's get in. And you can tell I'm a millennial kid because it's a PowerPoint presentation. And that was essentially what everything was when I was at school. Like, do a PowerPoint presentation on this or that. And that's what I know, so that's what we're using. So, what do I mean by fish? What do I mean by fish aren't real? Fish are, it was a taxonomic term. Essentially, everything you think is a fish, and probably a whole load of stuff that you don't think are fish, were grouped by Linnaean taxonomy into the class Pisces, in reference to the Greek um, zodiac sign. But Pisces hasn't been a valid taxa since the 1950s. So when I say fish aren't real, we're talking from a cladistic stance, not a colloquial stance. So this thing on screen is a crucian carp. It's obviously a fish from a colloquial stance. And if you hear me use the word fish from this point forward, it's because it's a lot easier than using some of the other names that we have for the classes and clades and all that stuff. But yeah, when you go to the local chippy, you're still having fish and chips. And when you go to the aquarium, you're still looking at fish, among other things. When you go fishing, you're still catching a fish or a boot, depending on what you've got. Um, so yeah, this probably will affect no one who's watching this except those people who are really anal about cladistics or who, work in that field, or like me, who are both. Um, because that's the kind of person I am. I'm sorry. So before we go in, we need to talk about taxonomy. This is Carolus Linnaeus. He was a Swedish uh, scientist. He was also, interesting enough, a creationist. But he came up with the Linnaean taxonomy, and that is essentially the skeleton we have for classifying things today. Although we have moved on to the cladistics model, which we'll get to in a bit. But you've probably, if you've gone through secondary school or high school, for those people outside the UK, you've probably heard like the way to reckon the whole organization of kingdom, phylum, class, order, family, genus, species, and more recently domain has been put on top because things are a lot more complicated. And then between stuff like phylum and class, or family and genus, there's going to be subfamilies or superclasses, um, infraphylums. It's a lot more complicated than that. That is just essentially the slimmed down version. The problem with this taxonomy is it relies on primarily on physiology. So you'll look at your animals or your plants or your fungi or whatever and say, oh yeah, these look similar. They're going in a class together because that's kind of the level we're looking at today in regards to fish and the former clade known as Pisces. What it doesn't do is it doesn't look into fossil species. 'Cause at the time, Linnaeus didn't really have all that many fossil species to work with, and really didn't start becoming something people thought about until the early 20th century, 1910, I believe. Um, they started looking at, I think it's fossil insects and fossil birds, and how they weren't in any, or some of them weren't in any modern clades. And then when we discovered genetics, things had a paradigm shift again, and it became clear that the Linnaean taxonomy really good for skeleton, not great for the details. And what we consider a clade, is um, essentially everything from the last common ancestor, hypothetical or real, because we haven't found all the last common ancestors, um, and everything below that is in a clade. So a good one would be, I guess, dogs. Dogs are wolves, so they're part of the species Canis lupus. Domestic dogs are Canis lupus familiaris. And then both those wolves and those dogs and a whole bunch of other things are in the family Canidae, which contains a whole bunch of clades. Essentially, it's all wolves are canids, but not all canids are wolves. Um, and we will see with fish, something came along that broke the clade Pisces. It was already breaking, to be fair, before this thing came along, but we will get to that. That's quite near the end of this slideshow. I apologize. I don't know how long this will be, but we'll move on. So, what is replacing Pisces? Pisces was a class, so it's sort of like the top level, near the top level of categorization, and we have five at current clades that have replaced it. That's Agnatha, which is a hagfish and lampreys in the far left. The Placodermae, which are extinct, hence the little dagger sign. The Canthoidae, which are also extinct. And this is where the Greek is going to catch me out. Chondrichthyes, which contains the sharks, the rays, sawfish, guitarfish, and chimera. Um, and then the Osteichthyes, which, if you can think of a fish that's not a shark or a hagfish or anything like that, they're all going to be in there. Most fish, quote unquote, are in osteichthyes. In fact, most vertebrates are also in osteichthyes. It's a big clade. I suspect um, there'll be some surprises in there, which we'll get into again near the end. I apologize. But we're talking Agnatha. These are the jawless and boneless fish. So modern clades, it's hagfish and lampreys. And they both, as the name suggests, don't have jaws. Uh, they're not the only vertebrates to not have jaws, but they're the only extant ones, as far as I know. Um, but they also they're old. As far as vertebrates go, they are very old. Like going back to the Cambrian period, at least that's where we think the oldest agnathans are. They also have no paired fins, so it's very much a sausage or an eel-looking thing, although eels have fins. And no epidermal scales. Like these guys, especially hagfish, are slime merchants. But if I'm on the right window, oh, geez. Yeah, slime. So going to the slime merchant before we look at that horrible image on the right. Hagfish essentially leak slime when they're frightened, um, and it can be so much that it can potentially choke predators, not prey. They can turn a bucket of seawater because hagfish are a marine species, or a marine clade, into a bucket of slime very quickly. They're also scavengers, so they're not going around killing things, or at least not things that are already not dying. And then we've got the lampreys. That is a mouth of a sea lamprey. Um, it looks like something from a horror film. Those are quote unquote teeth, and that's because not all lampreys, um, but a good many of them are essentially parasites. Also predators, I guess, because they're actively hunting prey, latching on, and then chewing in, and then drinking blood, eating fats, that kind of stuff. The rest are herbivores, and they still have the suction cup mouth, but that is used for sucking onto a rock, um, chewing the algae off, and then also using it as an anchor point so they don't get swept away in the current, because these guys are not particularly active. Um, like a lot of fish are ectothermic, but these guys are more ectothermic than most. They don't do well, they do okay with the cold. They're just not very active in cold temperatures. And judging from fossils we have of at least the ancestors of lampreys, they started off as parasites, and then some of them developed into herbivorous lineages afterwards. So this is essentially what the first lampreys would have had as dentition, and then everything else lost it and became less horrifying. But I said lampreys and hagfish are kind of soft targets, hence the slime merchant nature of the hagfish. Not the case in ancient times. So in the Cambrian, you had interesting predators, and then further on to the Ordovician, the Silurian, and then the Devonian, you just get more. So you had early on, you had radiodonts, which we're we don't quite know what they're hunting. It now seems that they're eating soft prey in the water column rather than stuff like this, which is Cephalastis, which is an agnathan. It has all the agnathan traits, except it has this really durable armored head. Essentially a head shield. That's what its name actually translates to, head shield. Um, there was a bottom feeder. It's probably being a herbivore. It doesn't seem to be a duraphage. It wasn't eating hard shell things, but it would have been predated on by. Eurypterids, which are the big old sea scorpions, orthocones, which are essentially nautiluses that grew massive. There's the radiodonts as well, which potentially could have eaten these guys. There's probably a whole bunch of stuff we don't know. And then there's the near the Devonian and Silurian at the end of their lifespan. There are also this group, the placoderms or the placodermi. The name translates to head plate, and they had, well, like Cephalaspis, really thick, really armored armor on their heads. That's a little. Mm. But they were the first fish, in fact, the first vertebrates to have jaws, and those jaws were essentially extensions or repurposing of the first gill arch. And they are also the first vertebrates to have teeth, although not proper teeth. They're essentially serrations of the jaw. Um, that said, those serrations of the jaw are not things you want to be, bitten by. This is Dunkleosteus, which is the most famous of the placoderms. It lived in the Devonian period, and yeah, it is kind of, well, it appears in media a lot because of the big old sheer teeth at the front and the fact it's got this big old armored head. Um, and there's some dispute about how big Dunkleosteus is, but this seems like pretty good estimate. It's almost great white sized. Like most normal great white sharks are probably the same size as the largest Dunkleosteus. You still wouldn't want to be anywhere near this guy in the water because he is, or they are essentially the super predators of the day. Nothing is eating them apart from other Dunkleosteus. And we know they ate each other because you find essentially fossilized vomit from these guys with plating of Dunkleosteus, other Dunkleosteus in their bodies, in the fossilized vomit. But not all the placoderms were huge. This is both both Rheolespis. I'm sorry. Again, this is the fact that I do not speak fluent ancient Greek. Um, but this little guy, was about 30 centimeters long. It's found on every continent, including Antarctica. Like Dunkleosteus, it has thick old dermal plating on the head. But it's known from 60 species within the genus. Over 60, actually. And these guys did really well. They were open water super predators. They're plankton feeders. They're grazers. They're ambush predators. Essentially filling every niche that fish fill today. And as with the armored agnathans and the next group we're covering, they went extinct in the end of the Devonian, approximately 380 million years. And that's because this new, this not this new chemical, but oxygen levels changed in the atmosphere. Things got colder for a brief period of time, and if you're a specialist, any sort of big change like that is not good for you because you're more susceptible to the effects of those changes. That's not to say a generalist species, because both the Rheolespis looked like it's a generalist. It was sort of like a scavenger on the seafloor and the riverbed, because they went in both freshwater and marine environments. It's potentially because, yes, this is represented by over 60 species. There's not a lot of diversity in those 60 species. Essentially, if things change and you can't adapt in your niche, you're going to go extinct. And if you can fill multiple niches but not very well as a generalist, you generally survive extinctions better. Not always the case, but you are more likely to survive those extinctions if you don't specialize. Um, Also, being smaller for most extinction events helps as well because you need less resources. That's a big factor of why at the end of the Cretaceous, approximately 66 million years ago. Everything, a lot of the things over 25 kilograms just disappeared from living, and a lot of the stuff that survived was under 25 kilograms or had a really slow metabolism and could wait out the extinction. Like that one was a bad extinction. It's the second worst extinction. Um, but we don't actually have to talk about that too much, I think, in this stream. So yeah, we'll carry on. And this is the other group that went extinct at the end of the Devonian. Or at least they lost a lot of diversity at the end of Devonian. And that's the Acanthodi, and that translates to spiny sharks. This is Acanthodus in the image, and they are very shark-like, as the name suggests, except they had these barbs coming out, um, and they did survive the Devonian mass extinction. I don't know what I was talking about earlier, um, but after the Devonian, their diversity had taken a hit, and they started specializing into like freshwater niches because another group came along and filled the niches that they would have filled in after the placoderms went extinct, that they were beginning to fill in. Um, yeah. So the Acanthodi, the, the members, their clade overlaps with the Chondrichthyes. It looks as if um, the groups are paraphyletic. Essentially, the basal Chondrichthyes came from somewhere in Acanthodi, but because the groups diverged a long time ago, we put them as different clades. Um, so a good example of this is Doliodus, which is the image. Um, it looks really shark-like already, except for those spurs sticking out. And even then, we can kind of imagine some sharks having that. I know Port Jackson sharks have some spurs, not that long, obviously. There's a few others. Um, yeah, and the reason we're looking at this guy and thinking that it's a transitional form between Ancanthodi and Chondrichthyes is looking at the scales. So, um, the scales of sharks and rays and skates and all those guys are formed of dentine, and I believe I'm going this over this later, so I might be, robbing Paul to pay Peter. Um, and essentially, it's a modified, almost tooth, and the scales in Doliodus are halfway between what was seen in the Acanthodi, which is sort of like keratiny scales, and then dentine. And some of the osteichthyes also have dentine scales. I mean, sturgeon are potentially one, potentially a group. It's usually the stuff that's really sort of primitive looking, if not necessarily primitive. Um, I will get into that as well. We're getting closer to that. But chondrichthyes, yeah, again I mentioned the denticles. They're the earliest vertebrates with true teeth. So the teeth that we have, teeth that sharks have, um, they were the first. They're the first clade to develop those. Um, yeah, again, there's not much to say about sharks, uh, except it's more than just sharks in this family. It's skates, it's rays, it's swordfish, it's guitarfish, it's chimeras, which are a lot less impressive looking than the name suggests. This is a bowmouth guitarfish, and they kind of shows sort of like a ray becoming a shark in essence, but there's plenty of sharks that have become flattened and almost ray-like, so they go back and forth. I'll continue on. But the true sharks, the ones that we have today, are not that old. Like a lot of people say, oh, they've existed for millions of years without any change. That's somewhat true. Um, but uh, the sharks we have today, and again, I'm probably preempting myself, first appear in the Jurassic period. Same with raisin skates, actually. The chimeras are a lot older, or at least the things that we think are chimeras. Before the Jurassic period, we get things that some of the things definitely do look like sharks. Um, but there's the actual diversity in body shapes is pretty impressive. You get stuff that looks like rays, stuff that's eel-like, kind of like the modern frilled shark, but not quite, well, a lot larger for starters. You get these things that look like sharks, but they've got weird dentition or weird body shapes. For example, helicoprion, which the tooth wall in the photo comes from helicoprion, and you see some really weird models of it, of like that wall sticking out of the lower jaw, with that sort of buzzsaw like bit below the jaw. That's not actually how it was arranged. Um, it looks like now the leading theory is that it was inside the jaw, kind of like a buzzsaw, still like a buzzsaw, and that what we're seeing with the wall is just tooth replacement. So it loses a tooth on the top of the wall, and then you get more, you get the teeth shifting up, I guess. I'm not quite sure how it will work in this. We've got other stuff like Stereocanthus, which is called the ironing board shark, which is this weird structure on its fin. And if you see a weird structure that you don't know what it's for, it's probably used in some form of reproduction, either to show off the females or potential mates, or for, the actual mechanical breeding. A lot of these almost sharks, these things that look like sharks, go extinct at the end of the Triassic period. One clade persists, and that's the herbaeodontiforms. They will be important in how sharks develop. I'm just going to take a drink. So all our modern sharks are in Selachomorpha, which first appeared in the Jurassic period. And the herbaeodonts, they survived the Triassic mass extinction, and they were sitting in sort of the niches that extant sharks would fill. But the diversity of forms was very low at this period of time. And another thing is when a niche gets emptied, you can be the first person in that niche, but if you don't fill it the best, you're going to lose that niche. And this is why you see bursts of radiation in forms after extinctions. As soon as a niche gets emptied, there are about 10 or 20 things competing to fill that niche. And you get this sort of burst in speciation after extinction events until things settle down. Um, but yeah, the modern sharks, and putting quite marks, sort of managed to fill the niches that we now see them in. And Haberdonks were sort of relegated to living in freshwater environments. They did it really well, or well enough that they were, present at the end of the Cretaceous, where they went extinct. Um, but Haberdonks were not the only things modern sharks are facing, and that would be the marine reptiles. So first of all, ichthyosaurs and plesiosaurs. Then by the middle Jurassic, you've got your pliosaurs popping up, and also marine crocodiles. And then sometime in the middle Cretaceous, some of those groups drop off. Most of the crocodiles, the pliosaurs, and the ichthyosaurs, or some of them go extinct completely. And then you've got the mosasaurs coming in. So sharks were not, for the most part, apex predators. There's a few. Cretoxorhina, which is what the teeth is of, was definitely something that was competing for the top spot. It's called the Ginsu shark, essentially because it looks the edge looks like a steak knife from brand it's named after, ironically enough. And they were I know the best fossils are in the Nairobi Straits Formation in Kansas. And that's the other thing. During the Earth's long development, sea levels rise and sea levels drop. You will find marine fossils in places where are hundreds of miles away from the coast. So yeah, that's that. In fact, you'll even find them up top of mountains, and that's mostly because as tectonic activity goes on, as plates move around, you do get mountain building, and some of the mountains are really old. I know, I think it's the Rockies are really old, um, but some mountains are really young. The Himalayas are relatively young, despite being so tall. So you will find like salt deposits up there and clams and all kinds of other marine fossils. And that's because essentially the plates collided, forced the mountains up, and that's why you find shark teeth in areas like Kansas. I know they found stingray teeth in the Himalayas, so they probably found shark teeth. Shark teeth are really common fossils because they're very durable and they fossilize easy, and the sharks just lose teeth all the time. Um, yeah, we're going up to osteichthyes, and this is essentially every other fish that hasn't been mentioned. They first appear in the Silurian period. They're already looking kind of distinct, suggests they might be older. Um, and this fossil is EU or something like that. It's from China, which isn't a shock. And it's essentially showing the first. It's the oldest, well, one of the oldest osteichthyes we have a fossil of, with an articulated jaw, which is important in terms of the osteichthyes. And the main thing about osteichthyes is they have ossified bones. So all the other clades have a cartilaginous skeleton, which doesn't preserve very well. It allows for flexibility, but it rots down quickly. Like you don't get a lot of shark fossils that are not the spinal cord, jaws, or teeth. Where you do, it's generally because that shark has been preserved quickly. Oh, and this is the fish matrix. So essentially, every fish you can think of, which is not a shark, not a lamprey, not a hagfish, not a ray, and not a chimera, is in osteichthyes. And you've got some famous examples like sturgeon in the top left. You got flounder as well, which is the one below it. Mud skippers down at the bottom. Coelacanth, which is an interesting fish from the right under the eel, but above the fish that doesn't look like it has a head. But it's kind of transparent. And yeah, there's a whole bunch more, obviously, that I haven't been able to picture. If I got a representative from every clade, it would be five, six, seven, who knows how many slides. Um, but yeah, you've got some interesting stuff here. You've got your elephant nose fish, which is pretty cool here. Which is one of the knife fish, and they are the electricity generating fish. Really cool. Like I could sit and talk about this particular slide for hours, but people will get fed up. People are probably already getting fed up, and we've been recording for who knows how long. How long? Interesting. I don't know. So the majority of those fish on that slide, with the exception of the coelacanth, there's a lungfish on there and sturgeon, are teleocytes. And that's essentially fish which have a telescoping jaw. So when you see a goldfish feeding, and the jaw pops out, so suck prey in. That's essentially the teleost jaw structure. Um, the teleost first appeared in the Triassic period. It was a really gradual radiation, um, mostly because the niches were kind of hard to fill. We do get some interesting stuff. Leeds ichthys was this filter feeding pretty large fish. Um, but you get another burst of radiation of forms at the end of the Cretaceous going into the Tertiary. And that radiation of forms is probably because all your marine reptiles get wiped out. A lot of the fish, particularly in freshwater, get wiped out. And then suddenly you have got these open niches um, in multiple levels. It's not just like animals being impacted by this, it's plants as well. So as new plants evolve, new niches open up as for animals, and you get this group called the Percomorpha, and that most of the fish outside the ones we talked about are in that clade. It's probably going to be subject to splitting up as we look at genetics. At least that's what I think. That's generally what happens. Hey, maybe it'll be this super clade forever. But yeah, they first appeared in the late Cretaceous, and they get their burst of radiation after the KT extinction event 66 million years ago. Um, so within Osteichthyes, we have the Sarcopterygians, and these are the fish that sort of break the old Pisces clade. We're finally getting to why fish aren't real from a cladistic stance. The Sarcopterygians are represented by six lungfish and two coelacanths, but they were a lot more prevalent in the past. And the difference between why they're sort of put on their own within Osteichthyes is because of their fin bones. Um, oh, I thought I had another slide into it. Doesn't matter. Um, the reason why their fin bones are different is because their radial bones are fused, maybe not into one bone, maybe into two. It gives their fins a lot more fleshy appearance. Um, yeah, and that enough was enough to put those two groups in their own sort of clade together. But if we look at the genetics, um, coelacanths and lungfish are more closely related to another group than they are to the rest of Osteichthyes. Um, and that group is the tetrapods. And in fact, actually, ironically enough, the lungfish are more closely related to tetrapods than they are to coelacanths. So while a coelacanth's closest living relative is the lungfish, a lungfish's closest living relative is in the tetrapods. And this is a lungfish here. They're interesting. Something I didn't notice about no mention about Osteichthyes is the swim bladder that a lot of them have is actually evolved from a pair of lungs, like primitive lungs, like these lungfish have. So early on in their environment, they must have been living in really stagnant water and coming up to breathe atmospheric oxygen to survive. And then when oxygen levels in the water increased, it wasn't needed, and it became a buoyancy organ, which essentially does. It shows that when an organ is not in use, it can be repurposed for something else. So what are tetrapods? If they are, the closest living relatives to lungfish, well, there's a tetrapod talking to you right now. And all amphibians, all reptiles, all birds, and all mammals are tetrapods. And they're with paraphyletic with the Sarcopterygians. So in essence, we are all Sarcopterygian fish, except because the tetrapod clade is so large, it became a branch on itself, out by itself. Um, that still doesn't mean that we're not essentially fish. If you go back far enough, the earliest tetrapods like Tiktaalik here end up being in a clade with what would be modern lungfish, modern coelacanths. And it's because of the fact that coelacanths and lungfish are so closely related to us. For example, the coelacanths, even though they're further away, genetically speaking, from tetrapods than now to lungfish, they are more closely related to the tetrapod than they are to the rest of Osteichthyes. And because of that, Pisces, which is already on its knees, or whatever fish have for knees, I mean, some fish have knees, or at least a knee bone, um, was essentially scrapped. Like, the genetic information showed that a lot of these fish were not closely related to each other. For example, the chondrichthyes are not particularly closely related to their Osteichthyes counterparts. Neither are Agnatha, and even though we don't know where the Acanthodian and the Placoderms would end up, they're probably their own lineages as well. Um, so yeah, in conclusion, we are all fish. Fish is not a real clade, or at least not anymore, because of genetics, because of extinct fossil species. Um, yeah, so in essence, what I'm saying is the clade fish is not real, but you can still use it colloquially. I have used it so many times during this slideshow that it's probably not even funny. And I'm probably sure there's someone somewhere yelling at me for using it so often. But yeah, so this is essentially a question period. Um, I don't even know if anyone's watching. Hopefully someone saw this. Um, oh, and I should also point out that during the slideshow, you would have seen numbers in the text and in the picture corners. Those are references. There is a reference list on the next slide, or next few slides, really. Um, and with um, yeah, so that's and I will try and get these in YouTube somewhere, at least the documents. That's the Fish Matrix one. Um, yeah, and I hope you guys all had enjoyed. This did take a fair amount of time to sort of make. So these wouldn't be regular. I'm hopefully going to get better at speaking as well. I did somewhat consider maybe I should have written a script. Um, but in the end, I was like, nah, I'll just wing it. Um, anyway, hope you enjoyed. Hope I wasn't too annoying. And yeah, I will see you soon. Right.